I will start anyway slowly with a brief summary of what I did yesterday. Okay, so for those of you who were maybe not here or maybe slept a little bit, so the lecture of yesterday was about the Boltzmann equation, and I will just recall a couple of things about this equation. So this is a PDE, which has the following structure. So you have a transport term and a collision term. And so what is important about this collision term is that it's quadratic. And this is actually due to two properties. The first one is that you assume that the collisions are binary. Okay. And actually, there is something else that I didn't discuss much yesterday, but which is really important, that in order that you have that these binary collisions produce a quadratic term in F, you have a chaos assumption. Okay, and I will come back on this later on, but it will be something really important. Okay, which means that, so this chaos assumption means that the probability of having two particles with given states, say Z1 and Z2, is equal to the product of the probabilities. Okay, so that's really important. Of course, it's not, say, it can be an assumption, but at some point, if we would like to derive this equation from microscopic dynamics, then you see that this chaos assumption has to be proved in some, it's not an assumption, it has to be proved. Okay, so that's the first thing about this equation that I wanted to recall. The second thing is that this equation is irreversible in time. And this was expressed in the H theorem. So I just recall that you have that, say, the relative entropy plus the integral from 0 to t of the entropy dissipation, which is smaller than. Okay, so that's the second property that will be important and that will actually lead to some paradox that we will need to discuss. And the last thing, which is a bit more technical, but which is actually also related to this this chaos assumption and binary collision and so on, is the fact that we saw that it's complicated actually to construct solution of this equation, okay, because say the typical a priori bounds that come from physics are this L log L bound, okay, while here you have something which is quadratic, so meaning that if at some point you have a concentration, maybe it's complicated just to make sense of this term. Okay, so this is that there is the problem of say functional spaces and concentration. Okay, so we'll see that all these properties will pop up in the derivation of the Boltzmann equation when we we'll try to get it as a law of large numbers. So that's the second part of the course. So that's the program here is to start from a microscopic model, so just a dynamical model for particles, and try to get this Boltzmann equation as a kind of limit of this. Okay, so here we will start from the simplest possible model, which is the R sphere dynamics. So this is just like a very big billiard, okay? And so you have a set of small balls of radius epsilon, and you have n such balls, okay? So that's the system here. And we assume that the dynamics is given by just Hamiltonian equation, which are really simple. So dxi over dt, So xi is the position of particle number I, is equal just to its velocity. This is just a definition of the velocity, okay? And dvi over dt is equal to 0, okay? So no acceleration. Of course, this condition is correct, say, as long as you have no superposition, okay? No overlap, okay? So as long as xi minus xj is bigger than epsilon. Okay, so maybe the radius is epsilon over 2. Okay. Okay, so in other words, you see that this means that it's essentially of only transport, but with the with this non-overlapping condition. So this means that you have a transport in a domain which is just this dn, which is just a set of, say, xi vi or I between 1 and n, such that xi minus xj is bigger than epsilon for all I different from n. Okay, so you would like to write only free transport in this domain here. But now, of course, as this domain has boundaries, then you have to prescribe some boundary condition. Okay, so you add boundary condition. And these boundary conditions are just a specular reflection for billiard balls. Okay, so here you said that if at some point the two balls collide and they arrive with velocities like this, you would like that they, after the collision, they go like that. And you have that v prime I will be equal to vi plus vi minus vj, yes, minus n ij. And this n is just a normal vector here. Okay, so nij is just xi minus xj divided by So these conditions, actually, they are the only conditions that ensure that you have no overlap and that you preserve both the momentum and the energy. Okay, so actually this specular reflection ensure that you have no overlap and that you have conservation of momentum and energy. Okay, so for this is really the only way you can define this boundary condition here for just for two balls. Okay, and actually, if you change the balls in ellipsoids or different geometries, then it's not clear that you have a unique scattering that will ensure both the conservation, say the conservation laws, and the fact that you have no overlap. Okay, so that's actually a funny problem, but okay, this is not the problem that I will consider here. Okay, so now you see that we are almost done because so of course this condition is for x on the boundary of dn, and I will call this this boundary ij just because this corresponds to the fact that xi minus xj is equal to epsilon.
In principle, you have also boundaries where three balls touch.
So I will discuss this right now.
Will we be on the torus also?
Yes.
In which dimension you are going to be in any dimension? 1, 2, 3?
1 is not very good because then you see that you have, so it will be a dimension greater than 2. But for 2, this is something which is interesting, because actually I think dimension 2 is a little bit problematic in physics. But say when you derive this equation, so nothing special will happen. So this is something that we can discuss afterwards. Okay, so now thank you, Thibaut, for the question. So you see that, of course, when you have three particles, you can have troubles when three particles collide at the same time. But you can also have problems if at some point you have kind of accumulation point of collision types. Okay, and so there is a result by Alexander, which tells you that for almost all initial configuration, dynamics is well defined for all time. Meaning that you have no multiple collision and no accumulation point. And,
almost all has a meaning only if you have already assumed some chaos assumption, some initial probability.
No, that's for the Lebesgue measure. Yeah. And anyway, we will see that we will, so even though you don't assume the chaos assumption, you see that all the measures that we will consider are absolutely continuous with respect to the Lebesgue measure. So we will not charge one specific configuration.
Product Lebesgue measure, so it means decorrelated. No, it's the product of x, all xi.
Yes, the Lebesgue measure on this dn. Yeah. Okay, so this is of course something. So it's not very complicated to prove. Essentially, you have to look at very small time interval where you have only and say and prove that essentially it's very complicated to have two collisions in a very small interval, and you count everything, and then okay, you can prove this. Okay, this is not very complicated, but okay, that's of course important to say that the dynamics is well defined. And maybe something else that I would like to comment before looking then at a limiting process is the fact that this dynamics, of course, it's well defined, but you see that because of this multiple collision, actually, you have also, it's very unstable. Okay, so so you can see even with only two particles, you see that. So for small epsilon. Okay, if you start with two particles here, you see that. So imagine that here the distance between the two particles is of the order of say 2 epsilon or something like this. Then you see that in this configuration they will hit together, they will collide, and then they will be scattered. Okay, so in this configuration you have some scattering. And now if you just change the two particles, so just put this one above the other one, so you have almost the same configuration. Okay, it's almost the same because I just moved this one, say, from a distance of the order of 4 epsilon or something like this. And then you see that you have no collision. Okay, so of course, for further time, you see that the dynamics will be completely different. Okay, so if at one point, at one time, you have almost the same configuration, you just change a little bit one particle, so maybe of a distance of the order of epsilon, then everything will be different. Okay, and of course here I have just one collision, but maybe all the other collisions could be different. Okay, so of course, so this is not unstable in the sense of dynamical systems, because once epsilon is fixed, there is no problem. You can get a kind of continuity estimates for this system. But you see that for this epsilon, when epsilon is small, and it will be small because I would like to have a lot of particles in a box, so they have to be small. Okay, and then you see that all these continuity constants, they will depend strongly on epsilon, and so we cannot expect to have really stable trajectories. Okay, and this will be at the same time, it's a problem from the mathematical point of view because we like very much rigid system where we can track everything. But on the other hand, say from the more physical point of view, it's very good because this means that somehow you have some mixing. Okay, so this kind of instability is both, say, a pain from the mathematical point of view because we cannot track really the trajectories. It's very complicated, but it's also the reason why we can hope to have a kind of mixing and therefore a limit. Okay, so that's really something which is okay. Maybe at this stage this is just a remark, but it's something which is really important. Okay, so this. The question, actually, it's a question because it's something that we are not really able to prove. But okay, so that's the starting point. So this R-sphere dynamics, and now I told you that I would like to go from this R-sphere dynamics to the Boltzmann equation, and the Boltzmann equation is a kinetic equation, so a statistical description. So now, if I would like to have a statistical description, what I have to do is to look at the scaling limit. So of course, if I would like to have a statistical description, it would be better if the number of particles is very big. Okay, if I have just 2 particles, then maybe I should just look at the two-body problem, and that's it. Okay. So now there are a few comments. So the first one is that, and it's kind of obvious, if n is large, and I am in a fixed box, say of size 1 or size L to the D, then you see that the total volume occupied by the particles is n to the times epsilon to the D. Okay, so this is what is called the excluded volume. And you see that if this guy is of the order of 1, then essentially what you have to study is kind of packing problem. Okay, how you can arrange all the particles in a box. Okay, and so this is a completely different problem. This is not what I would like to study here. So this guy obviously has to be really, really small compared to 1. But you see that, say, from the physical point of view, this means that in the end you will have a fluid with no excluded volume, so that is called a perfect gas. Okay, so this Boltzmann equation cannot describe anything else than a perfect gas. Okay. Then there is another quantity which is interesting, which is what is called the mean free path. So that's the excluded volume. Now I will look at the mean free path. So this is the typical distance that a particle will have between 2 collisions. Okay, and the way you can compute this mean free path is just by looking at, say, what is called a Lorentz gas or something like this. So you have, say, obstacles of size epsilon to the D, and now you have just one particle which is moving in this lattice here, and you would like to compute the typical distance between 2 collisions. Okay, and so you see that the way this particle will see this obstacle. Now, if I'm in the framework of the particle here, I will just see like a cylinder. Okay, so the particles, what it will see during a time t is just a cylinder, which so the length of this cylinder is velocity times delta t. Okay, and now the section of this cylinder is epsilon to the d minus 1. Okay. So now okay, this v times delta t, if I would like to see some transport of the particles, if I want the particles to move, then it should be of the order of the typical length. Okay, so this is like L times epsilon to the d minus 1. Okay, and if I would like to see essentially one collision, say that the transport and the collision part are at the same order, which is the case in the Boltzmann equation. You see that the transport part and here the collision term, they are of the same order. Then I would like this L times epsilon to the d minus 1 times n, of course, because you have all the cylinders, to be of the same order as L to the t. Okay, so this means that I would like to have that n times L times epsilon to d minus 1, which is the total volume occupied by all these cylinders. So somehow be of the same order as L to the d. And this scaling here will ensure that essentially you will have, say, one collision per unit of time. Okay, so the mean free path is exactly this quantity, so you just simplify by so the lambda here, okay, it's L, let me check, it's it's 1 divided by n, d minus 1, and L to d minus 1. Yes, I think that's the, I will check. Yes. To the d should be length. Okay. Okay, so the Boltzmann, the scaling where you expect to have the Boltzmann equation is when this guy is of the order of 1. Okay, so this computation actually is due to Maxwell. Okay, so now and for all the rest of the lectures, I will assume that L, so the typical length, the typical size of my box is just 1. Okay, and so I will always assume that I'm in the Boltzmann grad scaling or low density limit, and so I will have this. That's what is called low density or Boltzmann grad scaling. Okay, and so maybe there is something that I didn't discuss yesterday is the connection between the Boltzmann equation and fluid mechanics. So I told you at some point that if you just integrate the equation against 1v and v squared, you get some kind of fluid equations. And now if you assume that the relaxation, so the part which is due to the collision here, is much faster than the transport part here, then you see that what you expect is that the relaxation towards a local thermodynamic equilibrium will be much faster than the transport. And so essentially you will have a gas which is almost everywhere at thermodynamic equilibrium, and then you can close the conservation laws. Okay, so maybe this is just a small remark here. Say fluid mechanics, fluid models can be derived from the Boltzmann equation. In the fast relaxation limit. So this is exactly the case when this mean free path here is much smaller than L. Okay, so that corresponds to the case when lambda is much smaller than L. Okay, and so.
Can I ask a question?
Yeah.
So I'm a bit confused. The equation on the left.
This one here?
Yeah, seems to tell us that lambda is over the L. From the definition of lambda.
From the definition of, yeah, that's the case that I want to consider.
Ah, okay, so this is different. This remark is goes.
So the mean free path is always this quantity here. And now what I say is that in the regime that I will consider now, I will assume that this lambda is typically of the order of 1. And I get the Boltzmann equation. If it's not the case, so if this lambda is different from what you get, is something like this. Is equal to L divided by lambda Q of FF. That's what you expect, actually. Okay, so if lambda is of the same order as L, then you see that you get the Boltzmann equation. If now lambda is much smaller than L, you see that somehow this part here will be penalized in the equation. And so what you expect is that somehow the dynamics is first that this guy has to be to 0, and so F has to be in equilibrium, and then you will see the slow part here, which is associated to the transport. Okay, so that's how you can connect Boltzmann equation and fluid models. But then you see, because you have this equation that you have, because you have this scaling assumption that you have no excluded volume, you cannot get any fluid model. Okay, so because you have no excluded volume, this tells you that you have what is called a von Karman relation. And this von Karman relation tells you that you have a relation between the compressibility and the viscosity of the fluid. Okay, so you can get either compressible model which are non-viscous, inviscid model. But if you have viscosity, then say necessarily the model should be incompressible. Okay, so for instance, you cannot get the compressible Navier-Stokes equation from the Boltzmann equation. This is not an asymptotic, say, a regime of the Boltzmann equation. So I think it's really important, because sometimes we say, I say, that this is part of Hilbert's sixth problem, but Hilbert's sixth problem is really, I think, to connect microscopic dynamics to fluid dynamics. And this, say, if you use the Boltzmann equation as an intermediate step between this microscopic dynamics and the fluid dynamics, then you necessarily focus on some specific fluids. So this is just a small comment. Okay, so that now we are almost done. So we have microscopic dynamics, we have a scaling here, and the last thing, in order to get law of large number, of course, we need a probability measure. Okay, so that's the third point. Maybe I will keep the most important information here. So the dynamics is just dxi over dt is equal to 0, vi, dvi over dt equal to 0 on dn plus specular reflection. And the scaling is just that n times epsilon to d minus 1 is equal to 1. Okay. And now we'll look at the probability measure. So you see that this is, here now we have a dynamical system which is deterministic. So I can prescribe the probability measure at time 0, but then I cannot prescribe anything because everything is just determined by the initial configuration. Okay, so the random variables here, they are just, say, the xi naught, vi naught, for I between 1 and n, which are the position and velocity at time 0. Okay? And then somehow this probability measure will be transported by the flow here. But okay, you cannot say, and of course you don't really expect that for when everything is fixed, you will preserve the properties of this probability measure, except for invariant measure, and we will see that there are some of them, but not so many. Okay, so as I said here, something which is important to get the Boltzmann equation is that, and something which is of course important to get a law of large numbers, is to have a bit of independence. Okay, so what we would like, in principle, is to have random variables which are independent and identically distributed. Okay, so that's what we would like to have. So at time 0, we can say, oh, I can impose whatever I want, not exactly whatever, because they cannot really be independent, just because they have to be in this Dn, and so there is a non-overlapping condition. Okay, so essentially the best I can do is to say, okay, I would like to take independent variables, so I would like f0 to be the distribution of one particle. Okay, so f0 is just a function of x and v. And what I would like to have is just that the distribution of the n particles is just this tensor product, so meaning that it's f0 of x1 v1 times f0 of x2 v2 times f0 of xn vn. Okay, that would be a perfect measure, and we would have independent and identically distributed variables. Okay, so but this is not possible, so I have to multiply this by the indicator function of dn, which is the exclusion. Okay, and then of course, if I would like to have a probability measure, I have to normalize this by the partition function. Okay, so that's essentially the best that I can do. Okay. Yeah. But because of this, you have no independence. So maybe I can, at this point, I should do a little bit of computation here. I will try.
So when you mean best we can do, is it like entropy-wise sense or something, or? It's
at this level, it's not very precise, but I think from the entropy probably perspective, I think it's the best we can do. Yeah, because anyway, you have to say you can put whatever you want here. You will always have this indicator function here. So I think it's difficult to have less correlation than this. Okay, so now what I would like to say that, okay, they are not independent, but it's not so bad, in the sense that if I look at finite projection of this measure when n is very large, essentially it's almost factorized. Okay, so if I look at finite projection, so I will define f0. So I will call this f0n. And now I take the marginal of order s of this, meaning that I will integrate with respect to all variables except for the s first ones. Okay, so I just look at, I take s particles and I look at the joint probability of these s particles. Okay, so you see that what you will have is just 1 over the n. So you have the f0 to the s. Okay, and then you have to integrate f0 to the n minus s times the indicator function of dn d, say, z s plus 1, dn. Okay, so now in this indicator function, you can just look at different parts. So if you have first the indicator function of ds, and this one I can just put here. Okay, meaning that the s particles have to be you have an exclusion between these s particles here. Then you have the exclusion between the n minus s particles of the Q here. And then you have, of course, you have also the product of this indicator function for I, which is less than s, and j, which is bigger than s.
So you are computing marginals?
Exactly, yeah, not marginal for the s. Okay, and what I say that I can decompose this so I will just write this as this minus 1 plus 1, which should be equal to 0. Okay, and so for the part here with the 1, you see that what you have is, so now you have just the indicator function of d n minus s. So all this part here is just z to the of n minus s. Okay, so you get something like this. That it's the indicator function of s. And so the first part that you get is z minus n minus s over zn. Okay. And then you have another part. And essentially, for the other part, what you will use is this union bound, that if this guy is, in order that you get that this guy is non-zero, you have at least one I and one j, such that xi minus xj has to be smaller than epsilon. Okay, so typically you have a second term here that I will not write exactly, but so this term, what you expect is that you will have something like s times n minus s times epsilon to the d, okay, which come from this union bond. You choose the I, you choose the j, and then you have this the fact that you are in a small ball here, which gives you an epsilon to the d, and then you have another term which depends on, okay, it's not really important. Okay, so you can prove that times something that you can control here by z minus something which is controlled by this times z of n minus s minus 1. Okay, and this actually can prove just by looking at say, recursively, that you will have a control on this, which is in 1 minus, okay, I should write this because I don't know. 1 minus, so z minus s over zn is between 1 and the norm of, okay. And probably there is a 1 which is missing somewhere. Yes, the 1 which is here. Okay. Plus the term here. Okay, so anyway, you see that essentially this term will be essentially 1 minus 1 is almost 0, and then you get this one which is, so n times epsilon to the d minus 1 is of the order of 1, but say you get another power of epsilon here. Okay, so this means that in the end, all this quantity here is so yeah, I mean that's because I should remove the okay, so the minus 1 comes from here, and so this quantity here is of the order of epsilon. Okay, of course only in this Boltzmann graph scaling, because I assume that n times epsilon to d minus 1 is 1. Okay, so you see that in this scaling, you get that that essentially for any finite s, of course, you see that if s becomes very large, typically of the order of 1 over epsilon, this will be completely wrong. Okay, but say as long as s is finite, you expect the difference between this marginal of order s and the product here, the tensor product, to be of the order of epsilon. Okay, so it's not true that it's a chaotic distribution in the sense that everything is factorized, but asymptotically when n goes to infinity and epsilon goes to 0, you get something which is factorized. Okay, so that's okay. I will not do the computation in details.
You made a minus sign between the two terms. You say they are close.
Yeah, this is minus here and plus here.